Hello everyone, this is Jack Hassamon. Today I'll be talking about the first part of machining process. Basically, we will talk about fundamentals of cutting. We will talk about tool machining process, which is turning and drilling. As always, when we study each manufacturing process, we try to answer what does the process looks like, how does it work, why does it work, and what can go wrong with the process. Machining process is different from forming process. In forming process, we change the workpiece shape by changing its feature by applying force to change the workpiece dimension. Here, in cutting or in machining, we are actually removing materials from workpiece surface. We do this by producing chip or cutting chips. There are several machining processes that we will be studying. Here are just examples. We have straight turning, we have slab milling, and we have other processes also. Cutting tool tends to be harder than work material, and the cutting tool has complex three-dimensional geometry. The most important angle for the cutting tool are rake angles, which shown here as side rake angle and also back rake angle. This provides a kind of sharp angle so that the tool can plow into the workpiece. The cutting tool can be in one big piece, or it could be a small inserts where you can change the inserts from one corner to another corner when the tool or when the inserts wear out. The cutting tool creating the cutting chips. Basically, as the cutting tool plow into the workpiece start to come out as cutting chips. The cutting chips can curl and can get very long. Long cutting chip can damage the workpiece and can also damage the cutting tools. So many cutting tool is designed in such a way that there is a chip breaker so that it can break the cutting chip when the cutting chip gets longer. As we look at the slow motion picture of the cutting tool plowing into the workpiece, here there are a few things that we need to take a note at. First, we have a cutting depth. So this is the cutting depth where the cutting tool is actually removing this amount of work material. Now the cutting tool face has slightly complex rotation. So usually the cutting tool is actually rotating and also providing some kind of feed rate, uh, pushing, plowing into the workpiece. Here there is something called shear plane where the work material is actually, as the cutting tool is moving forward, the shear plane is moving forward, converting the work material from the left side, getting it to deform and becomes cutting chips on the other side. So in this particular case, the cutting chip can flow all the way up and keep going. So this shear plane is actually providing the energy to remove the work material. As an engineer, we are trying to control a lot of things. First of all, we can control the cutting tool itself. We can also control the work material. We can control the cutting parameter where we have cutting speed, feed, and depth of cut. And we can also decide on to apply the cutting fluid, and also we can design the kind of what kinds of machine tools that we want to use, and also the kind of work holding devices or fixturing to lock up the workpiece. And in the end, the result of controlling all this cutting process is that we can create a type of cutting chip. We can spend or apply amount of force and energy dissipated in the cutting process. Also, the temperature is rising very fast in cutting process, so we need to control that. And our tool can wear out quickly, and surface finish of the workpiece can also be very important in many applications. The cutting chip can be produced in cutting, as we note. Ideally, we would like to have a continuous cutting chip, smooth as possible. This is the way we want to control the process. Usually, in general, we do not like to have this continuous cutting chip or strange cutting form. Nonetheless, there is one thing that we need to take a note. When the cutting tool is getting very hot, the work material may start to melt and form something called build-up edge or build around the cutting tool tip. and this would change the tool geometry and affect how the cutting tool performs. The temperature in the cutting can rise very fast. So in general, if you think about the work material right in front of the cutting tool has the room temperature around 25 to 40 degrees Celsius. The temperature can go from 25 to 40 degrees Celsius all the way to several hundred degrees Celsius very quickly. And most of the heat generated by the cutting goes into the cutting chip. Some of the heat remains in the cutting tool and some of the heat remains in the workpiece. So in most cases when we do cutting, if possible, we would use some kind of cutting fluid to remove this heat. Most of the time when we do the cutting, either the cutting tool is rotating or the workpiece is rotating. And by having either tool or workpiece is rotating, the tool is actually slicing into the workpiece. And that slicing action is called oblique cutting. The inclination angle is making sure that the tool is slicing into the workpiece. This slicing action also creating the smooth uniform cutting chips. Now, in terms of cutting force, typically, if you look at the free body diagram of the cutting tool, we have two major forces. Number one is the thrust force, shown in yellow. This is where the cutting tool is actually pushing the workpiece downward. On the other hand, there is another force, which is cutting force, shown in green, pushing as the cutting tool is actually pushing the workpiece and creating the shape. So both forces are acting on the workpiece and creating the net force, which is resultant force R. But ideally, when we talk about the cutting power, we're actually focusing on the cutting force F sub C in general. Now, on the right-hand side is very important. It's the specific cutting energy, which is defined as the power required to remove 1 cubic millimeter per second of each work material. So we can estimate how much force or how much energy are required to machine each work material from this table. Engineers has also defined a manufacturing property which is called machinability. This machinability is defined by how good a workpiece or a work material can be machined. And this is described by how good the surface finish of the resulting workpiece, how much is the tool life that we can maintain achieve from machining that workpiece, and what are the force and power requirement. At this stage, we are not going to quantify this into numbers, but engineers have worked on this and try to classify workpiece into the level of machinability. Now, as what can go wrong, the first thing that can go wrong immediately is as the cutting tool is exerting a lot of force into the workpiece, the tool itself also gets to wear out. And this wear out can be shown in several ways. First of all, we can have something called crater wear, when the cutting tool will start to have some kind of dimples, or actually losing that some amount of material at the tool. That wear out process can take place in many cutting phase, many sides on the cutting tool. For example, it can have it on the flank face or on the rake face, and you can see this kind of one wearing out from a microscope. Taylor is the first person to study the tool wear mechanism, and based on his experimental studies, he have found that the cutting tool has the most significant effect on the tool life. So he developed the first Taylor tool life equation as V times T to the power of n equal to constant. So V is the cutting velocity or cutting speed, and T is the tool life. The unit could be in minutes or could be in seconds, but usually it's in minutes. And n is the exponent, which is based on the tool material. C is the constant. So for a pair of workpiece and for a pair of work material and cutting tool material, we can conduct the experiment to identify N and C. From that, we can estimate how much, by using certain velocity or certain speed, how much the tool life can be. Now later on, this Taylor tool-life equation is extended to cover the depth of cut and also the feed rate. Depth of cut is shown as in D, and depth of cut is shown as in F. Again, X and Y and N are all determined through experiments. So based on that Taylor tool-life equation, V times T to the N equal to constant. If on the x-axis is the cutting speed and on the y-axis is tool life. So as the cutting speed goes up, tool life will go down. And this depends on the cutting tool material. So A, B, C, D, and E represents each kind of cutting tool material. And one can see that basically the cutting tool E would have the longest tool life. On the x-axis, if you plot this graph on the log plot, we would get the graph similar to something on the right. And here you can see that by taking the log plot, the graph becomes straight line, and the slope of this graph would be the exponent n that we discussed. Now, the cutting speed and the feed rate are very important, because you can select if we want to be very fast, we can try to select the high feed rate and high cutting speed, and that would create a really large severe deformation for the cutting tool. The tool will start to have a lot of cratering on the cutting tool, so the tool would wear out very quickly. On the other hand, if you pick too low of the feed rate along with too low of the cutting speed, we would end up in another zone where the speed is too low, and basically we have a high heat, and that heat would generate the build-up edge on the cutting tool. So it's not good either. We want to be somewhere in the middle, where the cutting tool can last a long time. Now the cutting tool has certain parameter that we discussed, which is the nose radius on the cutting tool. Usually the cutting tool is not sharp, not completely sharp, so it has some kind of a nose radius. So this nose radius along with the cutting tool feed rate can create the feed mark on the workpiece, and this feed mark really creates something that we measure, which is called surface roughness. In some application, we want to make sure that the surface roughness is very small, smooth surface. So in that case, we would like to have a really low feed rate to make the surface smoother. Another many kinds of machining process that we will be discussing in this class. Some of them are turning. For the turning process, basically the cutting tool is actually moving along the workpiece. You can note that in this case, the workpiece is rotating, and the cutting tool is moving in straight line. So the turning process can have many variety of application. You can create something called tapering turning. You can create a certain profile by using more sophisticated tools. We can create something called external grooving. We can create a groove on the cylindrical workpieces. We can also use the cutting tool to remove the certain facing on the workpiece. So here again, notice that the cutting tool is actually moving across the workpiece face. In this case, we can also create something called face grooving. We can also having some kind of cutting tool in certain form to create certain profiles on the workpiece. We can create some kind of grooving. We can do the drilling process. We can also having some kind of cutting off to make in the shoulder, or some kind of grooving, threading, and even knurling when you create a certain profiles, certain patterns on the workpiece. The cutting tool has specific geometry, and these are usually the industry standard, where based on the left hand side, this is the workpiece, work material, and on the right hand side is basically certain kind of cutting tool where we have a high speed, the cutting tool made with high speed steel, and the cutting tool made with carbide inserts. So it has certain geometry angle associated with it. This is the popular one that tool manufacturers design and use successfully. We also have cutting fluid. Usually we, as I mentioned earlier, we try to use some kind of cutting fluid always to relieve the heat on the workpiece. And it could be comes in many forms. There are some synthetics, there are some oil-based cutting fluid. So this cutting fluid provides a lot of not only relieving the heat, but it also helps in flushing out the cutting chips remaining on the workpiece. So this cutting chip can cause some damage on the workpiece sometimes. So by providing the cutting fluid, we actually making the process smoother. The cutting lathe is probably the first thing that most of the machine shop will have. Basically, it's providing the kind of turning operation. The turning machine is done. This is a more of a manual machine where you have the spindle and you lock the workpiece, cylindrical workpiece here, and basically the spindle rotates. The cutting tool pulse basically will move. The workpiece may need to have not may be clamped by one side, or it can have another tailstock on the other side to lock or to lock the workpiece more firmly. So the tool post is here, and the tool can move along in both axes on the workpiece. This is another more sophisticated lathe machine where you have multiple turret lathe or multiple tools. So basically, we have a turret that can hold many different kinds of tools, so that we can clamp the workpiece and we can do several kinds of machining in one setup. Cylindrical workpiece can be clamped into the spindle by the use of collet. So the collet basically has some play around it. So basically the workpiece has to be in certain range to be able to put into this collet, and this collet can go into the spindle with the screw tightening. Another way of doing is also using the kind of mandrel to clamp the hollow workpiece together. Okay, and you can clamp this workpiece and you can do several machinings on you can do machining on several workpieces at the same time. Now let us take a look more closely at process parameter for turning process. As the workpiece is clamped with the spindle and the spindle is rotating with some RPMs. Here we represented the RPM with N. So basically the cutting tool is actually trying to remove the work material to change the workpiece diameter from the starting diameter d sub 0 into the final diameter d sub f. So this is represented by the depth of cut little d. Now, if you want to calculate the cutting speed of the workpiece, cutting speed of the tool, basically it's 2 times pi times r multiplied by n revolution per minute. Now 2 times r is the diameter, but here you can see that the diameter is changing from d sub 0 to d sub f. So we use the average diameter. So basically the velocity is pi d and n. That's the cutting speed, and multiplied by the depth of cut and multiplied by the feed rate. That becomes material removal rate, which is the amount of volume of material removed per unit time. This is very important for engineers to determine the cycle time necessary for machining the part. Here, in terms of feed rate, we can represent the feed rate in different form. We can represent it as an F, where the unit is in millimeter per revolution or inches per revolution, or we could convert that millimeter per rev into the linear velocity, where we have millimeter per minute or inches per minute. This can be done by multiplying f with the rotational speed n. We can also calculate the surface speed. Like I said, we can calculate by using the average, where we have pi times d and times n. The depth of cut is shown in the green area, where we're actually removing the workpiece, how much the cutting tool is going against the workpiece. On the other side, we have we have length of cut, where the cutting tool is feeding, going along the axis of the work material. and that is done by the length of cut. We can calculate or determine the length of cut, and we can calculate the amount of cutting time required for this workpiece. And finally, we also focus on the cutting torque, and basically the torque can be calculated by the cutting force multiplied by the radius of the axis and the radius of the workpiece, and here we use the average diameter again. From this torque we can multiply by omega, which is 2 pi n, to calculate the power required for removing material. So let's take a look at some example. Let's say we want to machine a 304 stainless steel rod with 6 inches long and ½ inches in diameter, being reduced to 0.48 inches. So we have d sub 0 and d sub f known. The length of cut is 6 inches L. The speed, rotational speed, is 400 RPM. 2 is using, and we have the axial speed of 8 inches per minute. We want to calculate the cutting speed, MRR, and power dissipated and cutting force. So to calculate the average cutting speed, basically we can calculate the cutting speed of in the beginning, outer surface where d sub 0, where we use d sub 0, and when inner surface where we have the final diameter, and we can calculate the depth of cut. Basically, if you have removed 0.02 inches, basically for the whole diameter, basically you have to split that by half just for the diameter, for the radius. So the depth of cut becomes 0.01, and the feed rate, if you convert the feed rate from 8 inches per minute divided by the revolution per minute, basically we would get the feed rate in terms of inches per revolution as 0.2. So again, we can calculate the MRR by multiplying pi times the average diameter by the depth of cut, which is 0.01, and the feed rate is 0.02 inches per revolution, and multiply by 400 RPM. So we get 0.123 cubic inches per minute. As we want to calculate the power required, let's take a note at the specific cutting energy. We look at the table, and here for the stainless steel, let us make a guess or some kind of assumption that the specific cutting energy for stainless steel is 1.47 horsepower minute per cubic inches. So that can be converted by multiplying with the MRR. So the energy or the power required to remove this amount of material to create 0.123 cubic inches per minute is 0.181 horsepower. Again, we convert this horsepower into pound inches by multiplying with the conversion factor of 396,000 pound inches per minute per horsepower. And then we divide that by omega, which is 2 pi n, and you get 29 pound inches. So this torque again can be converted into the cutting force that we want to calculate. So we solve the equation backward. The torque equals the part of F sub c multiplied by the average divided by 2. So basically we can solve this one for cutting force, and the cutting force turns out to be 118 pounds. So in terms of turning process, we would like to make sure that when we do this, when we perform the turning process, we want to make sure that the work piece is a fixture and held in a very good work holding devices. The blank or the original workpiece shape should be as close to the final dimension as possible, so that we remove minimum amount of work material as possible. We want to make sure that the cutting tool can travel across the workpiece without any kinds of obstruction. So when we design this operation, we need to make sure that the cutting tool, we have to simulate the cutting tool path, and we usually try to use commercially available cutting tools. What can go wrong with turning process? Many things. First of all, we would like to make sure that the tool doesn't interfere with the workpiece, and we support the workpiece rigidly, and we use the proper machine with good stiffness and damping capacity. This is not shown explicitly, but if you can imagine, the cutting tool is actually exerting a lot of force on the workpiece and work holding devices. So the machine structure is slightly very important to control the vibration of the machine. And the vibration is actually creating the problem with the surface quality of the workpiece if the machine is not stiff enough. And the tool can, in the uncontrolled or poorly designed process, the cutting tool can start to vibrate and have some kind of chatter where the tool can break, the workpiece material can also break, and causing the process to interrupt. Here is another version of a turning process where we use the cutting tool uh, doing some kind of turning process to create the threads. This is done by specific special tools to create the thread. The thread can be external thread and it can be internal threads. Another variation of the turning process, this is done very similar to drilling. This one is called boring, um, where usually we try to create a circular internal profiles of the hollow workpiece. So basically the boring tool is using a small inserts, and we are actually machining the internal surface of the workpiece to create specific profiles. Generally, after boring process, we would finish up by reaming process. This is the very typical process to create an accurate hole. Usually, we start by centering the hole, marking the hole center, and then we do perform the first drilling, and then we do the boring to uh, prepare the workpiece into the final hole sizes, and then we do the finishing operation with reaming. So reaming is actually very similar to grinding process where we have the multiple cutting edges and very fine uh, uh, cutting edges on the reamers. So this would create a good surface finish for the internal holes. Tapping process is another variation of creating the hole where we create the threads, internal threads inside the holes. The drills itself can also have very many variety. We have typical drilling process. We can have some kind of counter boring, spot facing, counter sinking, center drilling, reaming, etc. So there are many variation of the cutting tool that can be used to create. Now in this case is drilling. The drill itself has a variety of geometry. The most popular and the most basic one is a twist drill, where we have the spiral groove. This spiral groove allows the cutting chip to flow up against the drill and remove the cutting chip easily. So there are variety, as I said, there are variety of drills for specific purposes. Core drill is to use to make the existing hole larger. So if you have the hole and you want to create larger holes, we can use the core drill. The step drill is to create the hole with multiple diameters within the holes with different diameters. Counter boring or counter sinking is to produce depression on the surface to accommodate for the head of the screws or bolts. Center drill is to produce the hole at the end of the workpiece. Spot drill is to spot a start or to create a mark to start the hole at the desired location. Spade drill is to create deep holes. Crankshaft drill and gun drill are also creating the straight deep holes. So it depends on how we use for the application. The drill itself is very complex, so there are a lot of geometries going into the design of the drill. Here, I want to just point out that there are two important geometry that we want to pay attention to. First is the point angle, where it provides the kind of sharpness to drill into the hole. And the second one is the lip relief angle, where it allows the cutting chip to flow in this spiral and coming out of the workpiece. So both of them are very important, and we need to pay attention and select the proper angles for the right work material. Again, for drilling parameters, we want to calculate the material removal rate. Here, the MRR can be calculated by pi d squared divided by 4 times feed rate times the RPMs. The D is the diameter of the drill, and the cutting speed can be calculated by pi times D times N, as always. So let's take a look at an example. A hole is being drilled on a block of magnesium alloy with 10 millimeter drill at a feed rate of 0.2 millimeter per rev. The spindle speed N is 800 RPM. Please calculate MRR and torque on the drill. So the MRR can be calculated as from our equation. We know the diameter D, we know the feed rate F, and we know N. We can calculate that, and when we do that, it comes out to be 210 cubic millimeter per second. Now, magnesium alloy has a specific energy of 0.5 watt-second per cubic millimeter. So the power required, we can calculate that by multiplying specific cutting energy by MRR. So note that the unit get cancelled out and we are left with watt. So that come out to be 105 watts. So with this 105 watts, we can calculate the torque by dividing the power by 2 pi n, and n is 400 rpm. We convert that into second by divided by 60, and the torque come out to be 1.25 Newton meter. What can go wrong with drilling? So basically, the first thing that we should pay attention to is, again, the workpiece must be fixture properly, must be held properly, and basically we need to make sure that when you drill the hole, generally the drill would leave burrs on the bottom surface. So this may require some kind of finishing operation at the end. And because of the difficulty in chip removal, the drill should be retraced periodically. Even though the cutting chip can flow up through the spiral out of the workpiece, as a practice, the drill must be retraced periodically to remove the chip, and we also flushing the hole with cutting fluid periodically in order to help removing the chips. The dowel tool can create a cutting force. So in general, now most of the machineries we monitor the cutting force to see whether there's something wrong with the cutting tool. Many things can go wrong. For example, the drill can break while we are doing the drilling. The drill can wear out easily or excessive drill wear. The hole may not have good quality. The hole may have some tapering, or the hole can get oversized, and the hole can have poor surface finish. These are just a few problems with the drilling. There could be many more. For example, in some cases, you have the holes intersecting each other, and inside the intersecting holes, it's very difficult to control the quality. So here it is for today, and basically this is all I want to say for the first part of machining process. So if you have any other question, if you have any questions regarding the lectures, please feel free to leave your questions in the Google class, and I'll be happy to answer them. Okay, thank you. Goodbye.